a million names, and 20 guesses. So, where do the other 900,000 names go? Pattern 3 of 10 in the NBX STUDIO Dojo, binary search. The one where every single step throws away half of everything that's left. Read the question first, as always. The input is sorted, which is the precondition, and without it, none of this works. You're asked to find something, a value, or a position. Or you want the first or last thing that satisfies a rule, which is the sneaky version. Or the kth smallest, which is that shape again. If log n appears in the required complexity, the interviewer has told you the answer outright. Not sorted? Then sort it first, or pick a different pattern. Sorted plus find is the pair to watch, because sorted is what makes elimination safe. Scanning means checking every item until you hit the one you're after. On 10 items, that's up to 10 checks, which is nothing at all. On a million, it's up to a million, and on a billion, it's a billion. Binary search does 4 checks on 10 items, 20 on a million, and 30 on a billion. Look hard at those last two, because going from a million to a billion 1,000 times the data costs you 10 extra guesses. That's what logarithmic means in practice. You know this game already. A friend thinks of a number between 1 and 100, and every time you guess they say higher or lower. Guessing 1, then 2, then 3 could take 100 turns. So you guess 50. Higher. Then 75. Lower. Then 62. Every guess throws away half of what is left, and that's the entire pattern. Here it is on 10 sorted numbers. 2, 16, 56, up to 91, and we're hunting for 23. Same game, same rule. Guess in the middle, and let the answer tell you which half to throw away. 2 variables mark the edges of the range we are still willing to look in. Left equals 0 puts the low edge at position 0. Right equals len of nums minus 1 puts the high edge at 9. Right now the answer could be anywhere in those 10 positions, and that's the honest state of our knowledge. Every guess from here shrinks the range. 10 possibilities become 5, then 2, then 1. Watch the range, not the values. While left is less than or equal to right, keep guessing. Hold that equal sign. We'll come back to it. Mid equals left plus right, integer divided by 2. 0 plus 9 is 9, and 9 halved rounding down is 4, because those 2 slashes mean divide and throw away the remainder. So we look at position 4, which holds 16. Is 16 our target? No, 23 is bigger. And because the list is sorted, everything left of 16 is smaller still, so none of it can possibly be 23. Straight from the dojo. We found 16 at the middle, and our target is 23. 16 is smaller, so where do we look now? The left half, the smaller numbers. The right half, the bigger numbers. Or start over. Have a think, and pause the video if you'd like a moment. Ready? The right half, because the list is sorted, so everything left of 16 is smaller than 16, and 16 was already too small. So left becomes mid plus 1, and that plus 1 is the first bug people write. Why not just mid, though? Because we've already checked position 4, and it wasn't our number, so including it again buys nothing, and worse, the range would stop shrinking and the loop would spin forever. Left moves to 5. And look what one guess did. Position 0 to 4 are gone, including the 16 we tested. Half the list, and we looked at one of them. New middle. 5 plus 9 is 14, halved and rounded down is 7. Position 7 holds 56, which is bigger than 23. Same reasoning as before, mirrored. Everything right of 56 is bigger than 56, and 56 was already too big, so all of that can go too. The else branch fires. Right becomes mid minus 1, and the top edge drops to 6. 2 guesses in, and 8 of the 10 are already out of the running. Stop and look at the board for a second. The range is now position 5 and position 6, and nothing else. 10 candidates down to 2 in 2 guesses. 8 numbers were never examined, never compared, never even read. They weren't examined at all. They were eliminated by an argument, and the argument was simply that the list is sorted. Mid is 5 plus 6 halved, rounding down to 5. Position 5 holds 23. That's our number, so we return the index, and the answer's 5. 3 guesses for 10 items. For a phone book with a million names, that's about 20, and for every page Google has indexed, somewhere around 33. Doubling the data costs you 1 more guess. Every time forever. 1 more, and this line causes infinite loops in real interviews. Why the equals in while left is less than or equal to right? Because a range of 1 item still needs checking. because it makes the loop faster, or because it wouldn't compile. Have a think, and pause here if you like a second. Ready? A range of 1 still needs checking. When left and right meet, there is 1 candidate left, and dropping the equals walks past it. Almost every binary search failure is one of these lines, so learn them together. Left equals mid plus 1, never mid, because mid is already checked and leaving it in stops the range shrinking. Right equals mid minus 1, for the same reason on the other side. The loop runs while left is less than or equal to right with the equals, so a single remaining candidate still gets looked at. On very large arrays, left plus right can overflow, so left plus the half difference is safer. For lines, write them from memory. That's the whole surface. Get those right, and binary search stops being the pattern you dread, because everything else about it is the guessing game you already knew. For to go and do binary search itself, to get the template into your fingers. First, bad version, which is binary search on a yes or no answer rather than a value. Search in rotated sorted array, which is the one interviewers actually ask. And Coco eating bananas, where you binary search the answer itself rather than an array. 3 things to take with you. Your signal is sorted plus find, and sorted is what makes elimination safe. The move is to guess the middle and throw away the half that cannot hold the answer. And the bugs live in 2 lines, mid plus 1 and mid minus 1. Next in the dojo is the hash map, which is what you reach for when the array isn't sorted, and sorting it would cost more than the search saves. Go and do binary search first.